So before the break, just before the break, we had this wonderful idea called Green's theorem. So probably this problem will be something about Green's theorem. Let's see what the problem says. Let C be the closed curve, which consists of straight line segments between the points negative 3, 0, 3, 0, and 0, 3. So it's probably good to sketch this curve. So let's see, negative 3, 0 would be over here. 3, 0 would be over here. And 0, 3 would be up here. And so C consists of straight line segments. So it's these straight line segments here. It's a triangle. But of course, there's also the question about how do you move on C. And this gives an orientation. It says it's oriented counterclockwise. That's our preferred orientation, our orientation of choice. So we're moving along this curve in this fashion. Here is C. And we want to let f equal this crazy, inconvenient looking function. And we want to find the integral on this curve of f dot dr. Now, one of the things that we want to develop is sort of an intuition of when do we know what to use which tool? Because we have a lot of tools. And part of the problem is that we have sort of too many tools. And so we don't want to sort of like randomly try to apply tools unless it's the right one. So since we have a green theory mindset, what are we looking for? Well, for Green's theorem, the key to look for is you need to be in the plane, which we are. We're in the plane. And the other thing to look for is this. Now, that is referring to what? It's saying it's an integral on a closed curve. In other words, I'm going to start and stop at the same point. So when you see these two ideas, an integral on a closed curve, and you're in the plane, you think, aha, this is probably a good time to pull out Green's theorem. Now, what does that say? Well, it says the following. If I have an integral on a closed curve, C, of m dx plus n dy, that's equal to the integral over the region R of n sub x minus m sub y dA. Now the question becomes, okay, are we in the right setting? Well, yes, we do have an integral along a closed curve. But you might say, this is the wrong form. That's f dot dr. Well, here's the thing. We are going to write the same expression in multiple different ways. So the integral of f dot dr, this is sometimes written as the integral along the curve of f dot t ds, where t is the unit tangent vector. And it's also sometimes written as the integral along the curve of m dx plus n dy. So you want to be able to say, hey, I can recognize this in any context. There's lots of different ways to say the same thing. Now, where are m and n? M and n are these pieces. So m is the first part, n is the second part. So now we say, okay, we have all our pieces. And of course, one other question, you might say, well, what's R? Well, R is the region that's inside the curve. So that's what R refers to. So in this case, R is that actual solid triangle. C is the edge of the triangle. Okay. So we say, all right, let's apply the theorem. So according to Green's theorem, this will be the integral over our solid region, our full triangle here, of, I come to the second entry and take the derivative of that with respect to x. Well, if you take the derivative of this with respect to x, what do you get? 2y. This part, 1 over 1 plus e to the 2y, the part that we didn't want to integrate, we don't have to integrate. Oh, life is good. Okay, so 2y. Then we're going to subtract, go to the first term, take the derivative of this with respect to y. What do you get? Well, 2y. The cosine x cubed goes away, which is great because we don't want to integrate that. Derivative of minus x squared y with respect to y is x squared. Minus x squared. Got to be careful there with my signs. All right, and be very liberal with your use of parentheses. Parentheses save points. You'll notice the two y's cancel. Good news for us. Minus minus makes plus, which says that this is the integral over our region of x squared dA. And that already feels like a more comfortable integral to be faced with. It certainly doesn't have as many ugly parts. In fact, if you see something that says, oh, this looks really ugly, I don't want to have to deal with it. Probably you don't have to. If you use the tools, the terrible parts go away. But of course, this still leaves you with the question, how do you integrate this? You say, all right, well, it's just going back and using our tools of how to integrate over a two-dimensional region. So we should probably make a couple of notes here. For instance, the curves that are bounding our region, well, the bottom curve, that's easy enough to spot. That's y equals 0. This curve over here, well, this would be the curve x plus y equals 3, or if you like, it's y equals 3 minus x. The curve over here, why is it y equals 3 minus x? Well, the y-intercept is at 3, slope is negative 1. Over here, if we apply that idea, well, y-intercept is at 3, slope is positive 1. This is y equals 3 plus x. And now we think, okay, well, if we were going to chop this region up, we could chop it up vertically, but if we did, we'd have to change behavior halfway through, two integrals. That sounds like twice as much work as what I want to do. If we slice horizontally, life is a little better because it's always the same from top to bottom. So that says that this is an integral which works really well if we integrate this in the form dx dy. We say, all right, well, where does y go from? Smallest value is 0, largest value is 3, so it goes 0 to 3. And then where does x go from? Well, shouldn't have solved for y, should have solved for x. So that's x equals 3 minus y, and here it'd be x equals y minus 3. So I'm going from y minus 3 to y, where am I at? 3 minus y. So those are my bounds. Okay, cool. Well, what does this become? Probably more unpleasant than I wanted, but that's okay. We can handle that. No problem, no problem. All right, so integral 0 to 3, then this is 1/3 of x cubed, because I'm integrating with respect to x. Evaluate from x equals y minus 3 to x equals 3 minus y dy. So that's 0 to 3 of 1/3 3 minus y cubed. Subtract 1/3 y minus 3 cubed dy. Now, if you know, you can actually pull a negative out of this one. So this term becomes minus 1/3 y minus 3 cubed. So that when you put these together, this becomes integral 0 to 3 of minus 2/3 y minus 3 cubed. And now, this is actually not a bad integral. You don't have to do anything fancy. You don't have to multiply it out. It's just, y cubed, essentially. And so what do you get? Well, you get the following. Minus 2/3 times 1/4 y minus 3 to the 4th power. And then we're going to evaluate that from 0 to 3. So the 2 and the 4 simplify. Plug in 3. 3 minus 3 to the 4th is 0. Oh, that's interesting. That's different. Then we're going to subtract. And then here we have a minus 1/6. And then times that by negative 3 to the 4th. Because you plug in 0, 0 minus 3 to the 4th. And negative 3 to the 4th, that's 81. But we really should say you can cancel off a 6. Sorry, cancel one of the 3's with a part of the 6. And so if you are careful with your signs, minus, minus, minus to the 4th, that's going to go away. You're going to end up with 27 over 2. Again, one of your 3's canceled with the 3 and the 6, so you really have like 3 cubed, which is 27. The minus, because it's to the 4th power, it goes away. All right? So that's an idea. And so we're going to see this sort of same idea played out multiple times next week. Because yes, we have even more ideas coming next week. All right. But now for today. So today, we want to talk about what's called the surface integral. So I'm just going to go ahead and put this all up, and then we have time to digest it. So on the left are line integrals, and line integrals are things we've already talked about. On the right are surface integrals. Those are things that we want to figure out. So when we talk about a line integral, what's happening? Well, what I have is I have a curve. So it's parametrized, x of t, y of t, where I have t going between alpha and beta. And one of the things we did at the very beginning of the semester is we talked about length of a curve. We said, well, the length is integral from alpha to beta square root of x prime squared plus y prime squared dt. And we oftentimes refer to that as our ds. So ds is a little bit of length. And then we said, okay, so we have this notion of a line integral. So a line integral says I have this curve in the plane, and I'm going to integrate along my curve some function f of x, y, ds. And the way we do it is we transform everything into our parameterization. So it's alpha to beta, f of x of t, y of t, square root of x prime squared plus y prime squared dt. All right, so that's line integrals, and we've done line integrals before. Now, how should you be thinking about it? In some sense, there's a really special case, and I'll go ahead and use this picture down here to mark, is I can think about, this is like an integral, and I can think of there's some function. If you want, I can think of this as there's being a density function. So I have this wire here, and it's this bent wire. And I want to say, okay, how do I figure out what's the mass of this wire? Well, the wire has different density. So in particular, the density varies not just along how far along the curve I am, but where I'm actually at in the plane. So I have this wire, and I want to understand its density. Well, the challenge is our tools for integration are they're sort of basically built on simple one-dimensional ideas. And we want to try to understand that. So what we're going to do is we're really going to end up doing the following, is we use a parameterization. In this case, there's a very simple parameterization, which is you let x just be t and y be your function t. So what's happening is you're sort of creating, and you're saying, look, there's this integral here that computes density. I'm going to transform it to a similar integral between alpha and beta. So I can go from the curve into this alpha to beta by appropriately weighting things. And the way I appropriately weight things is I do it by what's the value of the function and what's this little piece of length. We want to do a similar thing now for surfaces, because we've done many of the similar processes. So when we talk about a surface integral, what we're really saying is I have this surface. So here's my surface down here. And now what I also have on this surface is I have a function. And I want to somehow say, what's the value of the function on the surface? I can think of density. Density is a really good intuition to help go. You know, how much mass is there? Well, all right, so how do we do this? We do what we do with any integration problem. Let's take what we're looking for, and let's break things into small parts. So we're going to take our surface, and we're going to break it up into small parts. So here, we break it up into small parts. And you say, all right, how much do we get from each part? And add the parts all up. Now, one thing we do is we say, what about the surface area? Have we done that? And we did. We did surface area. So we know how to find the surface area. We say that's the integral over our region R of the square root of f sub x squared plus f sub y squared plus 1 dA. So sometimes this is referred to as d sigma. I like to call it d of SA, just to say it's a little bit of surface. And then I'm adding them all up. So notice it's similar here. See, we're saying, all right, we're going, instead of going over our surface, here, if we think about line integrals, instead of going over the line itself, we're going over the parameterization. So it's like we're pushing down into the parameterization. Here, when we're looking for surface area, we don't actually go over the surface, we go downstairs. So downstairs is our region R. So that's our region down here. And what we're doing is we're saying, okay, I can work in this nice two-dimensional flat setting much better than this bumpy surface upstairs. So now when we want to do a surface integral, well, think about what happened before. I had a function times a little bit of length. Now I have a function times a little bit of surface. I'm adding up my pieces. So what I'm going to do is instead of working on the surface, I push down and I'm going to work over R. So everything has to be over my region. I rewrite my function. Well, g of x, y, and f of x, y. So what I'm doing is I'm parametrizing or rewriting so it's everything here is given in terms of the variables down in R. The same thing happened over here. See, we transformed everything to be in terms of t. All right, now what? Well, the DSA, that's a little bit of my surface area, so I say, okay, I just pull that part in. And that's how we do a surface integral. We just say, all right, let's just figure out what's each piece. Let's do a contribution. Now, what makes surface integrals hard? You're probably going to be able to spot it right away. It's this square root. You know, how do you deal with the square root? That's sort of been a nemesis of ours for a very, very long time. And the answer is very, very carefully. But we'll see there's one really beautiful case coming up in a few minutes where we don't have to worry about it. But before we get there, let's do an example. So, find the center of mass for the surface, which is the shell of the hemisphere of radius 3 above the xy plane, given that the density of the shell is equal to z. So let's be clear about what's going on here. So it's a hemisphere above the xy plane. So it's not the solid sphere, it's a half a sphere. And in particular, it's not even the solid hemisphere. What we're focusing on is we're focusing on that shell. So if it were an M&M, that's the candy shell. You know, we're not focusing in on that center. So I have this shell. And moreover, it doesn't have constant density. So my density varies depending on where I'm at. And in this case, it varies depending on z. So if I'm near the bottom, which is down here, I'm less dense because z is small. If I'm near the top, I'm more dense because z is large. And so the question is, all right, what's going to happen to my center of mass? Where is the center of mass of this object? Now, there are a couple things we can observe right away. Namely, if we look at our shape here, there's symmetry. And by that, we mean there's rotational symmetry. Now, rotational symmetry is very nice. Any kind of symmetry is nice, but I really like rotational symmetry. When you see that rotational symmetry going on, that's a signal that something has to be true. And in particular, what has to be true here, given that we have our rotational symmetry? Yeah, the x and the y are going to be 0 in the center of mass. In particular, we see that our center of mass has to lie on our axis of symmetry. In this case, it's the z-axis. So we know now that really we saved ourselves a lot of work. So we know what the x and the y coordinate are. That still leaves us with one coordinate to go. All right, so let's figure that out. So we need to find z bar. So the way you find z bar, it's a ratio. You divide something by the mass. Do you remember what you divide? What goes up in the numerator? mxy. This is the moment with respect to the xy plane. Oftentimes, you may not even remember exactly what goes in there as a name, but you'll be able to figure out what the right formula is. So let's go ahead. That means we get to do 2 surface integrals and not just one. Woohoo! 2. Nice. All right. So let's start with our mass. So if we want to do mass, what we do is we integrate on our surface. I'll call our surface G. I don't know why surfaces often get called G, but they do. So, all right. and we integrate density. Density dSA. So, how are we going to do this? Well, the key is we're going to do what we just talked about. Namely, we're going to rewrite this as an integral not on the surface, but as an integral over the region the surface lies. Now, the integral over which the surface lies is this disk here in the plane. So our region R is a circle. So we're going to transform this integral into an integral on the circle. So to do that, we have to do a couple of things. We have to figure out what's our density and what's our dSA. So we should probably do some things over here. If I look at this, it's a sphere of radius 3. So that would be x squared plus y squared plus z squared is equal to 9, 3 squared. So I want to rewrite this by solving for z, because I need to get my formula as a function of x and y. And we'll see why in just a second here. Z squared is 9 minus x squared minus y squared. And then when I take the square root, I'll get z is the square root of 9 minus x squared minus y squared. Now, normally when you take a square root, you get a plus or minus. Here we just want the plus, because I want to be on the top side. So I need the plus side. So in terms of what we just talked about, I'm thinking about this as my function of f of x, y. So the next thing, let's compute our dSA. Well, that's the square root of 1 plus f sub x squared plus f sub y squared dA. That's the formula for how you find your bit of surface area. So we start working on that. Well, f sub x. Now, really, if we were thinking about this, we were thinking about this as 9 minus x squared minus y squared to the 1/2 power. So it would be 1/2 comes down, 9 minus x squared minus y squared to the minus 1/2 times the root of the inside, which is minus 2x. And that's going to be squared. And now I see I definitely don't have enough space. So imagine this is a really big square root. So similar when you do y. 1/2, 9 minus x squared minus y squared to the minus 1/2 times minus 2y. And that's going to be squared. And all that multiplied by dA on the end. Now at this point, you might be getting a little bit nervous, but I hope you have faith that things work out. Because this is math. Beautiful things should happen in math. So, does anything beautiful happen? Oh no, our faith has been shook. Well, a little bit happens. The 1/2 and the 2's cancel. So that's good news. The minus signs won't really matter. So, apparently, I'm going to go on faith that we're going to have plenty of space here. So, if you write this out, the 1 stays as 1. But, notice that what will the next term be? You're going to get an x squared over 9 minus x squared minus y squared, because that minus 1/2 puts it downstairs, and the minus 1/2 and the 2 make it to minus 1. So the 1, I'm going to rewrite that as 9 minus x squared minus y squared over 9 minus x squared minus y squared in anticipation of the terms to come. So that's the 1. Plus, and the reason we did this is the next term will be x squared over 9 minus x squared minus y squared. What's the next term? Y squared over 9 minus x squared minus y squared. Which is, well, we have a common denominator. We add these all up. What do you get on the inside? Well, the numerator will be 9 over 9 minus x squared minus y squared. That's pretty good. That's probably about as simple as we can hope for. All right, so let's go ahead and figure out what's going on here. So our integral is the integral. Our density is z. So I'm just going to make that note here. So this becomes the integral. Now I'm going to go into our region R. It's the integral over our region R of what? Well, our z we have to replace in terms of x and y. But that's easy, because we have z in terms of x and y. So that becomes the square root of 9 minus x squared minus y squared. So there's our z. Our dsa comes here. So I'm going to go ahead, I can actually simplify that. That's 3 over the square root of 9 minus x squared minus y squared. Well, what happens? You get cancellation. So what are we integrating? Well, we're integrating 3. The 3 you can pull out. So that's 3 integral over your region dA. If you integrate 3 over your region, what are you finding? You're finding area, right? Your integral over your region dA is area. Do we know how much area there is in a circle of radius 3? 9 pi, right? Pi r squared. So that says we're going to get 3 times 9 pi, which is 27 pi. So that's our denominator. All right, well, we got lucky on that term. But we're not done yet, because we've got to get our numerator. Let's see what happens there. Well, our moment with respect to xy, that's our integral over our surface. It's similar to mass, but what you do is you add one more term. You can think of it as distance, or if you like, you can think of it as location. In this case, because we're talking about with respect to the xy plane, the distance would be z. So what we're doing is we're going to integrate over our surface z squared, because our density is also z. And if you do this integral, you say, okay, that's the integral over our region of square root of 9 minus x squared minus y squared squared times 3 over the square root of 9 minus x squared minus y squared dA. Yes? Now I can do a couple things. I can pull the 3 out, because that's a constant. And then I can do the integral over the surface, integral over this region, excuse me. We've already gone to the region. There's going to be 1 square root of 9 minus x squared minus y squared dA left. Okay, now we have something that we can integrate. Now, how can we integrate this? We could integrate in polar, or we can use our minds and say, we can do this without doing any integration at all. And you're probably like, what? I love that option. Okay, so how can we do this without doing any integration at all? The answer is, let's figure out what it means. Okay, so we're integrating over our region the square root of 9 minus x squared minus y squared. Well, what is that? You're integrating over your region what is currently being called z, which is the height. So I can interpret this integral geometrically as being the volume. It's the volume of the hemisphere. So I can use the fact that I know volumes of spheres to save myself work. Now, if you don't like to do that, you can go ahead and do integration in polar. You'll get to the same place. So if we use the fact that, hey, I can interpret this integral in a convenient way, namely it's half of the volume of a sphere of radius 3. So there's 3 times a half. The volume of a sphere is 4/3 pi r cubed. So what does that tell us? Well, it tells us we can cancel off some 3's here. 2 goes into 4. And then what are we left with? Well, 2 times 3 cubed would give us 54 pi. So that's what we get. So that's our numerator. So Now we have to do a little bit more math, and then we'll be done. If I take 54 pi, and I divide that by 27 pi, what do I get? I get 2. Therefore, our center of mass is about 2/3 the way up, because I start at 0, the top of it will be at 3. And so the center of mass is, well, we'll put it down here in this box, 0, 0, 2. Is it reasonable? I think it's reasonable, because certainly the dense part is near the top, so we should be slightly biased towards the top. And the good news is that 2 is between 0 and 3. If we had gotten an answer of 5, we'd be very nervous, because you can't have a center of mass be it so that your whole object is all on one side of your center. That's not centered at all. All right, so there's an example. Now, let's switch gears, and let's talk about something a little different, but also still related. So there's something called flux. Now, flux is a very fancy way of saying flow. I think it's actually a fancy Latin way of saying flow. So when we talk about flow, oftentimes we think of like fluid flow, but you can think of it as, say, airflow. Maybe you have wind. You can think of it as electrical flow. You have charge moving through a system. But something is moving. And what you want to do is you want to say, okay, I have this surface, and I want to figure out how much is flowing through the surface. So one way you can think of it is you can think of it as, I don't know if this is a great analogy, but imagine that this is a river. So to help you imagine, I'm going to label it in such a way. See, now it's clear that it's a river. You might say, but Steve, that's green. These are the banks of the river. Okay. So on this river, you want to understand how the water is moving. So what you do is you install this little sort of gate down here, and it's this mesh. And what you're doing is that the mesh has sensors that monitor how the water moves through the mesh. So I can think of this gate here as being a surface, and what's happening is it's measuring the flow at each point. And then the question becomes, well, what's the total flow of the water through here? Well, the answer is I have to figure out what's the flow at each point. And I'm going to do the following. I break it up into little tiny pieces. Of course, if I have a grid of sensors, my pieces just correspond to the sensors, and then I add it up. But the question is, okay, how do you figure out what the flow is at a single point? Well, so for that, we do the following. So we're going to need n. So n, you might remember, is oftentimes used for normal, and it's still used for normal here. So n is a unit normal vector to the surface. And then we have what's our motion, the thing that's moving. That's F. So F is the flow. So if I look at F dot n, what this is this is essentially the projection of F onto n. And what's being measured here is how much is moving through at that location. Or rather, I should say, what's the rate at that location? To get how much, I need to multiply it by an area. So F dot n is the rate. DSA, so rate times area, that gives us our flow. So F dot n DSA, that's how much is moving through at each location, and now I need to add it all up. So we get that the flow, or the flux, it's the integral on the surface of F dot n DSA. Now we're going to focus on one special case, and this is the case that we are going to have you worry about. We can do other cases, but this is the one that we want you to be able to handle. Namely, suppose our surface isn't just any surface, it's our surfaces of the form z is a function of x and y. So these are the things that we've talked about before when we talked about surface integrals. So I need to figure out, okay, what's my normal vector? Well, the nice thing about this is we've done this before. We said, okay, we can find normal vectors to surfaces. And in particular, we know that gradients are perpendicular to surfaces. So what we do is we say, all right, let's look at the surface z minus f of xy. Because I can think of z being equal to f of xy is the same thing as z minus f of xy equals 0. So if I take the gradient of that, I'm guaranteed I'm going to be perpendicular to my surface. And it becomes, take the derivative with respect to x. There's only one x. That's f sub x. And there's a minus sign. Take the derivative with respect to y. There's only one y with a minus sign. Take the derivative with respect to z. There's only one z. And you get 1. Now notice this 1. This one is convenient in that it says that whenever you look at a normal vector, it's always going to be pointing a little bit up because it has a positive z component. So these are what we call upward pointing normals. So you'll sometimes see something saying refer to upward pointing normals, and it's referring explicitly to this. Now this is perpendicular to our surface, but it is not our normal vector we need because it's not a unit vector. So easy to solve. Make it a unit vector. So you divide by the magnitude. And if you divide by the magnitude, you get your f sub x squared plus f sub y squared plus 1, square root of that. Now you're probably thinking, we just saw a square root of f sub x squared plus f sub y squared plus 1. But notice that this one is downstairs. Perhaps something nice will happen. Well, here we go. So if we put all this together and say, all right, I have a surface, z equals f of xy over region R. Through this surface, there's a flow being modeled by some function capital F. That's a vector field. And I want to figure out what's the total flow through the surface, given that I have upward pointing normals. Essentially, when you talk about upward pointing normals, what you're doing is you're giving an orientation to your surface. And orientation matters. We'll talk more about this probably next week. Orientation is important. So here we go. So we know that the flux, it's the integral on our surface of f dot n dsa. It's right there. We just copied it. And we know how to compute f dot n because f, it's a vector valued function. It has usually 3 components, m, n, p. We're going to dot it with our vector n, which we copy from here. In our DSA, we computed before. That's the square root of f sub x squared plus f sub y squared plus 1 dA. And now, you see that very similar to line integrals, the terrible parts cancel out. The square root, the things that are annoying, are gone. And what you're left with is something very clean and simple. So it becomes the integral of your region of minus m times f sub x minus n times f sub y plus p dA. So it makes it a much easier thing to work with. So in case you're wondering what's happening down here, is you'll see that these green arrows are actually the unit normal vectors, and you see that they vary over time. So down here in this corner, it's pointing pretty straight up because you're fairly flat. But as you move up to this corner, it's almost starting to point, it's not pointing exactly sideways, but it's starting to point very much in a sideways direction because the amount of change in x and y is fairly large compared to what's happening. In other words, f sub x and f sub y are fairly large. All right, so you'll notice, by the way, that there's a box around this formula. When you see a box around a formula, that should be a signal. I should memorize this. So let me just say that again. There's a box around this formula. All right. So let's do some examples. Okay, let's see. So I look for my piece of paper here. So find the flux for f equals x times I plus y times j plus z times k for the surface with upward pointing normals given by z equals 1 minus x squared minus y squared above the xy plane. This sounds like a complicated problem when you see all these words. There's flux, there's upward pointing normals, there's all these surfaces. But remember, there's a simple formula. If you remember the formula, it doesn't become so scary. So the formula says, what we're going to do is we're going to integrate over our region of minus m fx minus n fy plus p dA. So what we have to do is we have to identify what are m, n, and p. what's our function f, what's our region r, and once we have all those pieces in place, we just put it together and life is good. Now m, n, and p come from your f. So here's m, n, and here's p. So those are going to be given to you. Your z corresponds to your surface. Sometimes you have to solve for it, like when we had the sphere. Sometimes they just give it to you. So here, this is our f of x, y. Our r, that wasn't given to us. So we have to figure it out from context. So we say, okay, what do we have going on here? Well, let's think about what this surface is. 1 minus x squared minus y squared. Do we know what that looks like? Suppose we start with this one. X squared plus y squared. What does that look like? What? It's been a long break. It's a bowl. That's the paraboloid. So z equals x squared plus y squared. That's one of our classic examples. Now let's sort of build on this. Suppose I said z equals minus x squared minus y squared. What have I done? I flipped it upside down. So now whatever was in my bowl just got spilled out. So suppose now I tack a 1 on to the front. What have I done? I moved it up by 1. Okay, so there's my bowl now. So now I want the part of the bowl that's above the xy plane, because there's that phrase, above the xy plane. That was my clue that that's the part I was looking for. So I say, okay, well, what's that? Well, if I cut it off at the xy plane, what will end up happening here is I will come down, and what's the shape at the bottom? It's a circle. Can we be even more specific about this circle? Like, for example, does this circle have a special name? It's a unit circle. Now, how do we know that? Well, to figure out where it hits the xy plane, set z equal to 0. If you set z equals 0, you get 0 equals 1 minus x squared minus y squared, or x squared plus y squared equals 1. So our region is the unit circle. So that's our region R. So now we can put this all together. This says integrate over your region R of the following. So I'm just going to go along and put in what we need. Minus m, which is minus x, times f sub x. What is f sub x? Negative 2x. Minus n, which is y, times f sub y, which is negative 2y, plus p. Now what is p? You're probably saying, Steve, you're pointing to it. It's z. Why do you make it sound like it's a complicated answer? Well, do I put plus z here? And why not? I need in terms of x and y. See, z is not in terms of x and y, it's z. So how do I make it in terms of x and y? I use the function. See, there's this z equals. So p is going to become 1 minus x squared minus y squared. There we go. So there's my minus m fx minus n fy plus p. Well, what do we have? We have 2x squared plus 2y squared plus 1 minus x squared minus y squared. So this becomes the integral over our region of 1, and then it'll be plus x squared plus y squared. Okay, so this one, I do think we have to go and convert into polar. So if we do this really quickly, because we do want to do more examples, the more examples we do, the better we're going to understand things. So it's a unit circle, so no surprise, our bounds are theta goes 0 to 2 pi, r goes from 0 to 1. Our function becomes 1 plus r squared, and dA becomes r dr d theta. Well, there's no theta on the inside, so I could actually push the theta over to here, the d theta, so I get a 2 pi. If I integrate this, first off, multiply the r through, So you'll get the integral of r is 1/2 r squared. Integral of r cubed would be 1/4 r to the 4th. And then you evaluate from 0 to 1, you'll get 3/4. So you get 2 pi times 3/4, which is 3 pi over 2. I did that last part really quick, but there's no real surprises at this point. All right. Let's try another one. Find the flux for f, which is 3y comma x comma 6, for the surface f of xy equals x plus 3y squared minus xy with the downward pointing normals over 0 less than or equal to x less than or equal to 1 and 0 less than or equal to y less than or equal to 1. And they really made an emphasis for the word downward. Okay, so that says you flip your orientation. When you flip your orientation, what do? Flip your orientation changes your sign. All right. So we can actually still use our same formula. We just say because it's downward, toss a negative in. So negative, integral of our region of minus m fx minus n fy plus p. All right, that's not any big surprise. We have our region is given here. Our function's given there. There's our m and p. And again, you can be given vector-valued functions in two different ways. You sometimes I, j, k, sometimes as just the entries in this sort of vector format. So we put this together. So this is going to be equal to minus, well, all right, integral over our region. Let's see what this becomes. Minus m, so that's 3y. F sub x, what does that become? Well, 1 and minus y. Minus n, which is x, times f sub y. Well, that's 6y minus x. And then plus p, well, which is plus 6. All right, so there's our integral, dA. So if we clean this up, what do we have? Well, minus 3y plus 3y squared minus 6xy plus x squared plus 6. And, well, I don't know. I'll put the minus through. Plus 6xy minus x squared minus 6 dA. At this point, it's a very simple integral because it's 0 to 1, 0 to 1. Once you have the setup, life is good. Because I do want to take just a moment to talk about one idea. Not because this is going to be important. There's nothing that's going to be boxed here. In fact, there's even a disclaimer at the very beginning. If you look, there's this asterisk. Go down here. It says this will not be tested. But it's good to know things. It's good to know things. You don't have to, just because you're not tested on it doesn't mean it's not important to know. So there's this notion of what's called the parametrized surface. See, just like we had parametrized lines. So before, we might have had this curve, and we said, okay, here's this curve. I can parameterize it, so then I can explore it and understand things better. And what you were doing when you had a parametrized curve, you basically just sort of straightened it out and said, I'm going between alpha and beta. So we might want to do the same thing with the surface. Because there are sometimes there's surfaces where we can't really solve for z as a function of f of xy very simply. So as an example, you might have a cylinder. So this is a cylinder, and you say, well, the problem with the cylinder is you can't solve for z as a function of x and y. But what you can do is you can say, look, I'll take this region, and I can imagine mapping it in a way that I form a cylinder shape. So we can do this in general. So I can do a parameterization of a surface. So I have r of uv is the x, y, and z, depending upon u and v. And the thing is that everything translates over just as you would expect. You just make everything in terms of u and v. So you make your functions x, y, and z in terms of u and v. You integrate over your region in your uv plane. The only thing is, how do you handle surface area? And it handles in the way you think it should be done. So you do it the magnitude of RU cross RV. They might say, I don't think that's the way it should have been done. Well, that's the same idea we did when we did things like Jacobian. It's that type of principle in play. we should probably do an example. So again, our key idea here is that we can parameterize our surface. We're really trying to take a two-dimensional flat thing and move it up into a three-dimensional setting, which is perfectly fine. I mean, we've done this before. It's the same process as what we've done with lines. So not really a different concept. We're just knocking it up by one dimension. And after all, it's multivariable calculus. We do want to go up by a dimension or two. So let's do an example. So G is a cylinder of radius 1 with height 1 sitting on the xy plane. And it can be parameterized by r of uv as cosine u sine u v. So if you think about what's going on here, so cosine u sine u, that's our circle. So it's saying that in xy it's behaving like a circle. Then, and notice that's one variable, then the other variable is the height. So if we were thinking of this as being our u direction, and this part as being our v direction, then it really is what we were talking about before, where we're taking this and we're wrapping it around and forming it up. So that as u varies, we move around our cylinder. So now we have a nice parameterization. And see this cylinder, you can't write this as z as a function of x and y, because you have all these points stacked on top of each other. Can't be done. Can't be done. But now, because we can wrap things up as a cylinder, no problem. Life is good. So our goal is to determine the mass. Now really, we're just using density and mass as sort of stand-ins, as functions that we might want to think about integrating as sort of a motivating factor. It's not that somehow everything is a density and a mass. It's just that that's something that we can sort of intuit as to what's going on. So let's think about what we have. Well, our key here is use the formula. Well, that's a pretty good plan. I like that plan. So we have that the integral on our surface G, of our case, our function G is our density function, delta of x, y, z, dsa will be what? Well, it's going to be the integral on our surface of 1 plus x squared z dsa, which becomes what? Well, our region is going to be given in terms of u and v. Because this is not, yes, we do have a cylinder. So you might think, wait a second, shouldn't our region be the unit circle? But it's not, because see, where does this surface lie on top of? It's not on top of the unit circle, where I think of it as a filled in circle. It's literally on top of the edge of the unit circle. So we can't do our region as the unit circle. That doesn't make any sense. But our region here is in terms of the parameterization. All right, so this is going to become the integral over our region, and figure out what that is in just a moment. 1 plus x squared, so that's cosine squared u, times z, which is v. Then I have to multiply it by my dsa. So we've got to figure out what that is. So that's going to be the magnitude of, we take r sub u is minus sine u, comma cosine u, comma 0, cross r sub v, which is 0, 0, 1. All right, and then that'll be our dA. So we got to figure out what is this cross product, and then we have to multiply it by that, and set up our bounds, and hopefully life will be good. Well, I hope so. I hope so. So, all right, a little bit of work ahead of us. A little bit, but we can do it. We can do it. So let's see what this would be. So we've got our I, j, k, our minus sine u, our cosine u 0, and our 0, 0, 1. Now, the good news is there's so many zeros that almost all our terms are going to disappear. For instance, what do you see? Well, we have an I times a cosine u times 1. So that's a cosine u in the I component. A j times a 0 times a 0. A k times a minus sine u times a 0. All right. A 0 times a cosine u times a k, that's a 0. 0 times 0 times I. and 1 minus sine uj, which is sine u, and there was nothing in the k. So that's the cross product, and the magnitude of this would be the square root of cosine squared plus sine squared, which means that this is 1. All right. So that says that we're going to do what? Well, we're going to integrate over our region, and now we'll put in our bounds. 0 to 2 pi, 0 to 1 of 1 plus. The way you integrate cosine squared is you replace that by 1 plus cosine of 2u over 2, power reduction, and then times v. And then we integrate dv du, because these are our v bounds, these are our u bounds. So if we integrate that, we get the integral 0 to 2 pi, and here we'll get v plus 1/4, 1 plus cosine of 2u times v squared, because there's a half, and then v squared over 2. And we evaluate from v equals 0 to v equals 1. Well, nice thing is v equals 0 is easy to evaluate, so is v equals 1. Plug in 1, you get 1 plus 1/4 times 1, that makes 5/4 plus 1/4 cosine 2u du. And what does that become? Well, that's 5/4 u. And then here, 1/8 sine of 2u, because the integral of cosine is sine, and I have to divide by 2 because of the inside. And then we're going to evaluate from 0 to 2 pi. Well, if you plug in 2 pi, 5/4 times 2 pi is 5/2 pi. Sine of 4 pi is 0. Plug in 0, you get 0 and 0, which means our answer is 5/2 pi. So it works out really well. So the point here is that we can do these things. It is possible to work it out. You just have to be careful. And so this is a nice idea, and one which, depending upon where your future takes you, you might want to work in parametrized surfaces. Because parametrized surfaces can handle things where you can't solve for z as a function of x and y. Well, that's okay. We don't have to. Now, since we have a little bit of time, let's quickly shoot back for just a minute. Let's actually finish this integral here, because we didn't finish it before, and there's always that desire for completion. So what does that give us? Well, it's integral 0,1, integral 0,1 of our expression 3y minus 3y squared plus 6xy minus x squared minus 6 and dy dx. And so in the interest of space, I'm just going to do this really quickly. All right, so integral of dy. So I'm going to integrate and then evaluate right away. So here, it would be 3/2 y squared. Evaluate from 0 to 1. That'll leave you with 3/2. Here, it'll be y cubed. Evaluate from 0 to 1. It'll leave you with 1. Of course, don't forget the minus. Minus 1. Here, it'll be 3xy squared. Evaluate that from 0 to 1. Leaves you with 3x. Here, it'll be minus x squared y. Evaluate that from 0 to 1. That leaves you with minus x squared. And here is minus 6y from 0 to 1. That leaves you with minus 6. All right, and we're integrating that dx. So we'll do this again. So 3/2 minus 1/2 is a half. And if I integrate that, that'll be a half x from 0 to 1, which is 1/2. That's the first two terms. 3x, that'll become 3/2 x squared. Evaluate that from 0 to 1. That'll leave you with 3/2. Minus x squared, well, that'll become minus 1/3 x cubed. Evaluate that from 0 to 1, and that'll become minus 1/3. Minus 6x, evaluate that from 0 to 1, leaves you with minus 6. 1/2 plus 3/2 is 2. Minus 6 is negative 4. And if you subtract a third from negative 4, you get negative 13 over 3. Or really, which is negative 4 plus a third. Or is it negative 4 minus a third? But the answer is negative 13 over 3. All right. So one more problem. You've recently been hired to help design rides in an amusement park. Oh, that sounds like a great job. I wonder how I can get that job. Anyways, one of the rides you are working on involves a large saddle-like surface on which people will be strewn into. In particular, the surface is z equals x squared minus y squared, for 0 less than or equal to x squared plus y squared less than or equal to 4. Now you're working to ensure the supports in place will be sufficient to support the structure. In particular, the design calls for the density to increase with distance from the middle. So delta of xyz is x squared plus y squared. Estimate the total mass of the surface. Well, that's not so hard. We just think about, okay, how do you find mass? In any case, it's always the same thing. We integrate, and because we're looking for mass of a surface, two-dimensional thing, so integral over our surface, we'll call it g, of our density, dsa. All right, good. That's right. That's it, right? Yeah, that is it. Now we just have to sort of work this out. Well, that's the integral over our surface of x squared plus y squared dsa, because our density is x squared plus y squared. Now, how do we actually handle this, though? Well, the way we do this is we think about, all right, what's our region? Well, they gave it to us. It's right here. It's 0 less than or equal to x squared plus y squared less than or equal to 4. Okay, so we know what our region is. So what we need to do is say, okay, this is equal to the integral over our region of, write everything in terms of x and y. The good news is x squared plus y squared, already in terms of x and y. Saved ourselves a bit of work there. Our delta SA, sorry, our dSA, excuse me, becomes what? Well, it's the square root of 1 plus fx squared plus fy squared dA. Where, what is f of xy? Well, that's this part over here, x squared minus y squared. So this is going to become 1 plus 2x squared plus minus 2y squared. Okay, so that's 1 plus 4x squared plus 4y squared. Now look at this problem. We say, you know, there's an awful lot of x squared, y squared action going on here. So let's transition. So our region, x squared plus y squared less than or equal to 4, our region R is a circle of radius 2. So we're going to transition, since we see x squared plus y squared everywhere and we see a circle here, we can say, all right, that becomes an integral. Let's do polar coordinates. X squared plus y squared becomes r squared. Square root of 1 plus 4x squared plus 4y squared becomes the square root of 1 plus 4r squared. And then our dA becomes r dr d theta. Theta, full circle, 0 to 2 pi. R, 0 to 2, so radius 2. Now this looks a little bit challenging, not so clear, but say, hey, suppose you let u equal the inside. U equals 1 plus 4r squared. Then du is 8r dr. So you can move the 8 across, put it here as 1/8, and notice you have an r dr, which is very convenient. In the meantime, notice the inside has nothing to do with theta. You can really put the d theta over there. So the integral from 0 to 2 pi d theta, that's 2 pi. And then we have the integral. Well, let's update. 1, because put in r equals 0, you get 1. Then put in r equals 2. Well, 1 plus 4 times 4, 17. And now what do we have? Well, that'll become square root of u. That's easy. Square root of u. You're the 1/2. R dr. Well, that becomes 1/8. I'll put the 1/8 out in front. Du. And then, oh, wait a second. challenge. What do you do with r squared? Because we got to account for everything. We've accounted for the rdr. We've accounted for that square root of 1 plus 4r squared. We took care of the theta stuff. Got the bounds. What about r squared? The answer is, we solve for r squared. See how there's an r squared here? So r squared is equal to u minus 1 over 4. So u minus 1 over 4. Now I can pull the 4 out again. So what does this become? I already have a 2 over 8. That makes a 1/4. There's another 1/4. So that makes that pi over 16. Integral 1 to 17 of, multiply the u to the 1/2 through, u to the 3/2 minus u to the 1/2 du. So this becomes pi over 16, and then we integrate each piece. 2/5 u to the 5/2 minus 2/3 u to the 3/2. Evaluate that from 1 to 17, which is pi over 16 times 2/5 17 to the 5/2 minus 2/3 17 to the 3/2. Subtract 2/5 1 to the 5/2 is 1, and 2/3 times 1 to the 3/2, which is 1. And that is about as simple as we can get. Yes, sure, we could add those together, but 17 to the 5/2, hopeless, hopeless. And there are some other things you can do, but at this point, this is those times, rare times, where it's like, maybe a calculator would be good. So, all right, well, that's it for now, and tune in next time when we do some more. Have a good day. Bye.